Hello, my name is Joe Steele, and I would firstly like to thank you for attending my presentation, which is in conjunction with the 2021 Tyndall and IPIC Summer Internship Communications Workshop. I will today be performing a simple demonstration of total internal reflection in optic fiber cables. The study of optics has been going on for many centuries, but in recent times, due to discoveries such as lasers and advances in technology, it is now one of the most exciting and innovative fields of research, no more so than optical communications. The backbone of optical communications are optical fibers. These are flexible wires made of high-quality glass, otherwise known as silica or plastic. These are very thin and usually thinner than the width of a human hair. These optical fibers have become increasingly important in communications and transmitting information across the world. Here we can see a map of the various optical fibers which are connected to every country on Earth. Optical fibers transmit light from one end to the other, and in other words, they transmit information. Optical communications has many advantages, such as a broad bandwidth, which means that they can transmit many types of information simultaneously, such as audio, video, microwave signals, and much more. As well as this, optical fibers are both an electric insulator and they're immune to electromagnetic interference. This means that optical fibers are a very versatile way of transmitting information. So, how does light travel down these optical fibers? It is done by a mechanism known as total internal reflection. So total internal reflection can occur when light travels from a medium with a high refractive index, such as perhaps water or glass, into a medium with a lower refractive index, and the usual example there is air. As you can see on the diagram, light rays coming out of, for example, the blue medium, which has a higher refractive index, can be reflected completely back into the medium at a sufficient angle of incidence. So this angle of incidence, which causes total internal reflection, can depend on both media. This is how light can travel along an optical fiber. So you can see there on the diagram that the light just bounces inside along the walls. The optical fiber has a slightly higher refractive index than the cladding outside of it. So, this is how we can demonstrate how total internal reflection occurs inside of two media, one with a higher refractive index and one with a lower refractive index. So, all you need for this demonstration are a water bottle with a hole punched in it, a laser pointer. You can see that I got one from a pet shop, so no high-tech equipment required, and some water, and of course a tub to catch all the water that will be pouring out. So all you have to do is pour in some water into the bottle and allow it to empty out of the hole. Now the tricky part, you want to turn off the light so it's pitch dark and try and shine the laser through the hole and see what happens. And now I've just put together a video of myself performing this demonstration. It is a small bit tricky to get right, but definitely worth it. And as I was trying to keep this as low-tech as possible, some of the results could definitely be improved upon. But we can see that in the pitch dark room, the laser is being shined through the bottle and out of the water which is pouring out of the hole. And you can see that the light travels down the water, which is exactly what occurs inside of an optical fiber. One tricky part to this is trying to get the water to flow out of the hole in a laminar fashion. It is a bit turbulent here, which does make the light a small bit messy going down the hole, and that is definitely something that you could try and improve this demonstration with. And that concludes my presentation on total internal reflection in optical fibers. I would like to thank you all for your attention.